Hello student, how are you? I hope you are very well preparing for the examination. By the way, I am Dada PRS from SSS Government First Grade College, Chennagiri, Davanagere University. I would like to discuss today is the problems on diffraction of the 4th SEM physics paper of Davanagere University. Let's we go discussion one by one. Hello, here is the first problem. A narrow slit illuminated by a light of wavelength 5890 angstrom and is located at a distance of zero point 0.1 m, that is A, from straight edge. If the measurement are made at a distance of 0.5 from the edge, calculate the distance between the first and second dark band. So you are seeing that here is the wavelength is given, and small a is given, and b, the distance between the edge and the screen. The formula for the nth dark band is xn is equal to square root of root b into a plus b 2 into n lambda by a, and usually how meaning a is the distance between the slit and the straight edge, and b that should be the distance between the straight edge and you put this value. A is 0.1 meter, b is 0.5 meter, and lambda is meter. Then you will get the value, put this value here, and this is the equation for the, seeing that this is the equation for straight edge. Band, the distance between the band is given by root 1, and put this for second and first one, because the first and second order. And calculate for x2 minus x1, put the n value is 2 and n is 1, and simplify it, and then you get root b, this value root 2 minus 1 come, n is come out of this, and root n. So in this way 2 minus 1, put this value, and we got the value of this x2 minus x1 is equal to 0.7786 into 10 to the power of minus 3 meter. This is the distance between the first and second dark bands. And further we go to for zone plate. So problem is, what is the radius of the first zone of the zone plate of focal length of 0.2 meter for a light of wavelength 500 angstrom. Here is the lambda is 5000 angstrom, and that is 5 into 10 to the power of minus 7 meter, or 5 into 10, 5000 into the power of minus 10 meter, and focal length is 0.2 meter. And if r1 is the radius of the first zone, then f1 is equal to r square by n lambda, that is the n is equal to 1 is the first order, that is r1 square by lambda, n is equal to 1 into lambda is lambda. Then we need r value, that is equal to square root of fy, and this is value given the 3.16 into 10 to the power of minus 4 meter, or in centimeter if it is 0.0316 centimeter. And we move further related to the same half period zone or of a zone plate. Determine the radius of a first half period zone of a zone plate which behaves as a convex lens of focal length 40 centimeter and for a wavelength of 4000 angstrom. Similarly, the r1 is square root of nfy, but n is first one, hence it's a 1. So this is value is given by 4 into 10 to the power of minus 4, that is 4.4 mm. Next one, a zone plate has focal length of 50 centimeter at a wavelength of 6000 angstrom. What will be its wavelength at lambda is equal to 5000 angstrom? Here is given focal length. If the wavelength 1 is given, then its focal length is 50. If what will be happen if the wavelength is changed 6000 to 5000 angstrom? f1 is 50 centimeter, let lambda 1 is 6000 angstrom, and let lambda 2 is 5000 and find f2. But we know that the formula is f is equal to r square by n lambda for the first one, and f1, put this for f1 and f2, then we get f1 is equal to r square by n lambda 1 and f2 is equal to r square n lambda 2. Comparing both these two, and n get cancel and r get cancel, there is does not need any radius, so f2 by f1 is equal to lambda 1 by lambda 2, that's f2 equal to f1 into lambda 1 by lambda 2. So we get this one and put this value of given, and we got 60 centimeter, and this is the focal length if the wavelength changed from 6000 to 5000 angstrom, and focal length remains constant. And move further example. Similar way, if the focal length of zone plate is 1 meter for a light of wavelength 5 into 10 to the power of minus 5 centimeter, so what will be the focal length for the wavelength 6 into 10 to the power of minus 5 centimeter? Usually similarly way, there is the f2 is equal to f1 lambda 1 by lambda 2, then they put this value and we got the 83.3 centimeter. Similar way, next one, the radius of the first ring of zone plate is 0.5 mm, and if the light wavelength is 5894 angstrom falls normally on it, where should the screen be to be placed to get bright spot? Here is our R1 is given, and it is in millimeter, and it converted to meter, that is 55 into 10 to the power of 5 meter. Lambda is wavelength is given, so 5894 10 to the power of 10. As the light falls normally, it is parallel to the axis of the zone plate, and after pegging through the it will meet at the axis at the points. Then the focal length is at 50, and r1 square equal to n lambda. For the first order, it's usually n is equal to 1, so you got r1 square equal to n lambda. This value is gives to 0.51 mm or 51 centimeter. So this is to be screen should be placed at a distance of 51 centimeter from the zone plate. Focal length is nothing but is the distance between the lens and the converging point. The converging point is on the screen, and is lens is zone plate is behaves like a lens. Is the distance, that is the distance. Don't be confused with the focal length. Focal length is the definition is the same thing. The distance between the screen and this point means a converging point to a lens. As we move further, the innermost half period zone has a diameter of 0.5 mm. Find the focal length of the plate if the lambda is, that is wavelength is 550 nanometer. Here is the distance d is given 0.5 mm and r is equal to 0.25 mm. Then f is equal to r1 square by lambda, and put this value and you will get this lambda is equal to 11.4 centimeter. As we move, next we related to Fraunhofer diffraction, a single slit. Let's see example. In an arrangement of Fraunhofer diffraction, we use a slit of width 0.2 mm, and first minimum is at 5 mm on either side of the central maximum. If the distance between the ends and the screen is 2 m, that is the capital D, calculate the wavelength of light. If x is the distance between the secondary minimum from the center of the principal at maximum, and is the distance, then we see that x is equal to lambda d by a, where x is given 5 into 10 to the power of minus 3 and d is given 2 meter, means the distance between the screen and the lens, and a equal to 0.2 mm means 2 into 10 to the power of minus 4, the width of the slit. Then lambda is equal to ax by d, and the value, put this lambda is equal to ax by d, so 2 into 10 to the power of 4 and 5 into 10 to the power of 1 divided by 2, that's equal to answer lambda is equal to 5 into 10 to the power of minus 7 meter. So some next point is the grating constant. Grating constant is nothing but when there is a slit, number of slit is there, this is the width is a and opaque distance is b. When both is add a plus b, that is from ear to ear, that is called grating constant a plus b. And related a plus b sin theta is equal to n lambda. So related to some problems about this. A parallel beam of sodium light is allowed to be incident normally on a plane grating having 4250 lines per centimeter, and a second order, that is n equal to 2, of spectral line is observed to be deviated through a 30 degree. Calculate the wavelength of the spectral line. So given is the theta is given for the second order is 30 degree, lambda 2 going to be find out, and n is 4 to 50. Here is a plus b is not given, so a plus b can be given by a plus b. A plus b is equal to 1 by n, hence a plus b equal to 1 by 4250. So then grating constant a plus b sin theta 2 lambda, that is lambda is equal to sin theta, so 4 into 1 divided by 4250 into 2, that is value is given, you can calculate 5882 into the power of minus 8 centimeter, that is 5882 angstrom. Hence this is the wavelength of the spectral line calculated. A parallel, next one, a parallel beam of monochromatic light is allowed to be incident normally on a plane transmitting grating having 500 lines per centimeter, and a second order spectral line is found to be diffracted through 30 degree. Calculate the wavelength of light. We know that a plus b equal to 1 by n, that is 1 by 500. Sin theta is equal to sin 30, that is 0.5, 1 by 2, that is order of second order. Then it is a, this is the second order, hence n is equal to 2, and we can find the calculate the wavelength of light. And this is the formula. A plus b sin theta is equal to 2 lambda, or lambda is equal to a plus b sin theta by 2. Put this value, a plus b is 1 by 500, 1 by 500, sin theta is 0.5 and divided by 2, that is 5 into 20, that is 5000 10 to the power of minus 8 centimeter, that is 5000 angstrom. If it is converted into centimeter to meter, it is 5000 angstrom. So move further. In a plane transmission grating, the angle diffraction for a second order of maximum wavelength is 5 into 10 to the power of minus 5 centimeter, and the angle is plane, the angle of diffraction is 30 degree. Calculate the number of lines in 1 centimeter of the grating surface. Here n is the number of the lines per centimeter. We know that the formula a plus b is equal to 1 by n. Here is the second order is given, n is equal to 2, theta is given 30 degree, lambda is given 5 into 10 to the power of minus 5 centimeter. We formula is a plus b sin theta into lambda theta. Put this value, a plus b means 1 by n is equal to 2 into 5 into 10 to the power of 5 into 5, that is n is equal to 0.5 into 10 to the power of 4, means 5000 per centimeter. Put this value a plus b here, so you can get the value. Further, a wire grating means wire is used as a lines of a grating. So wire grating is made up of 200 wires per centimeter placed at equal distance apart. The diameter of each wire is 0.025 mm. Calculate the angle of diffraction for the third order spectrum and also find the absent spectra, if any. Wavelength of light is used here is the 6000 angstrom. Given lambda is given, write down this one. A plus b means 1 by n, that is 200 wires means n is 1 by 200 centimeter, that is 0.005 centimeter, and the for the order is third order diffraction for third order, so n is equal to 3. The third order n is equal to 3. We know that formula a plus b sin theta is equal to n lambda. N is 3, that's why 3 lambda. Theta 3 means n order, that is sin for third. A plus b into 3 into 1 by n, that's the multiplier. So 3 into value is 0.00360, and sin of this value is given 2 degree 4 minute. The width of opacity means opacity is the wire is the opacity, so diameter of the wire is 0.025. so and width of transparency, so I'm already seen the grating constant a plus b, that is 2, but 0.0025 is the b value. Then you can calculate the a value, so a equal to 0.0025. Subtract this value and we got the value. So order is present, so grating element divided by the transparency, that is a plus b divided by a is given 2, and this shows that the second order spectrum is missing in this experiment. In this value, for this value the second order is missing one. Move further, show that in a diffraction grating with the grating element is 1.5 10 to the power of minus 6 meter grating element, and light of wavelength 550 nanometer, and third and higher order principal maxima are not visible, so it's apply for the one. Let's see given is the lambda 550, lambda is 550 means 5500 times a plus b is given. We know that for higher order, let n be the maximum number of orders of the spectrum that can be observed with the grating. Since the maximum of angle diffraction is 90 degree, so 90 degree means sin 90 is 1. The maximum positive order is n, so n is equal to a plus b by lambda theta by lambda, sorry, n is equal to a plus b by lambda. 1.5 into 10 to the power is value is 2.72. Only second order will be visible, higher third order and fourth order not visible here. As we move further, calculate the angular dispersion in degrees per angstrom for a diffraction grating having 14,438 lines per inch when used in third order at 4,200 angstrom. Here is given, order is given, n is equal to 3 for the third order, lambda is given, so 4200 angstrom. Number of lines per inch, number of lines per is 14,438. Inch means the grating constant can be given, ap is equal to, here is given not centimeter, here is given is the inch. Inch means 2.4 into 10 to the power of minus 2 meter. So 1 inch is equal to 2.1 inch is equal to 1 inch is equal to 2.4 into 10 to the power of minus 2 meter. Hence a plus b equal to 2.454 into 10 to the minus 2 divided by this line, and you got the grating constant. The distance between any opacity and the transparency is 0.1759 10 to the power of minus 5 meter, and formula is sin theta is equal to n lambda by a plus b. put this value n third order lambda value a plus b value, and we got the value 0.7163 is the sin theta. But cos theta, you know, cos square 1, we know that cos square theta plus sin square theta is equal to 1. So cos theta is equal to 1 minus sin square theta, that is 1 minus square root of 1 minus here, okay, the cos square theta plus so cos square theta plus sin square theta is equal to 1. Put this value and we got the value 0.6955. Similar way we got the, so d theta, angular dispersion is d theta by d lambda, but n is the 3, d lambda is the 10 to the power of 10 in very smallest distance. So a plus b is 0.1759 10 to the power of minus 5, so into 10 to the power, and cos theta is 0.6978. Put this value, d lambda means 1 angstrom is equal to 10 to the power of minus 10. You want compare with the given 4200, that is d lambda, that is 1 angstrom we taken. So 0.002244 radian, and radian can be converted into degree, as we know that radian is equal to pi degree, means 180. As we move further, a plane transmission grating having 6000 lights per centimeter and used to obtain spectrum of light of wavelength 5890 angstrom. And at a normal incidence, when you see here is the normal incidence or big incidence. So here they calculate the dispersive power of the grating in second order spectrum. Here is the given, lambda is given 5890, and normal incident, and having 6000 lines per centimeter, means a plus b equal to 1 by 6000 centimeter, because 1 by n means number of lines per given, centimeter is given 1 by 6000 centimeter, and order is calculate the dispersive for the second order, that is n is equal to 2. So in this way, a plus b sin theta is equal to n lambda, we know that the formula. So sin theta equal to n lambda by a plus b, 2 into value, and we get the value 0.7068. And similarly cos theta equal to 1 minus sin square theta, and 1 minus, and the sin theta values can be substituted, so we got the 0.7074. and dispersive power is equal to d theta by d lambda. So n is equal to a plus b cos theta, where a plus b is 1 by n, that is, so 1 n into n, small n into capital N, cos theta ab value is 1 by n, as you can see here. So nn, because a plus b is equal to 1 by n, hence a plus b value is nn. Here is the n, cos theta, and value is 16963. It's the dispersive power of this grating. So move further, similar way, find the number of the lines grating should have to resolve the first order doublet having a wavelength difference 0.6 nm at 589 nm. D lambda is given 0.6 nanometer, 0.6 into 10 to the power of minus 9. So move further. Find the number of lines grating should have to resolve the first order doublet and having a wavelength of difference 0.6 nm and at 5893 nanometer. Is d lambda is given, so d lambda is 0.6 nanometer, that is 0.6 10 to the power of minus, and the first order, that is n is equal to 1, lambda is given, here is 5893, that is 5893 into the power of minus 3. If n is the number of lines on the grating to resolve the two wavelengths, then lambda by d lambda, that is resolving power of grating. Lambda by d lambda is equal to capital N into small n. Small n is the order. So n is equal to lambda by n into d lambda is equal to value. So n is equal to lambda by n in d to d lambda. Put this value, lambda value, n value, and d lambda value, we get 982 is the number of lines of grating. As we move further, what should be the minimum number of lines on a grating which will just resolve sodium light of wavelength d1 is equal to 5890 angstrom and d2 5896 angstrom in second order. Here is the given the two resolving wavelength d1 and d2 and take this mean wavelength, that is value is 5893 angstrom. Get the difference between from maximum to, and the difference is maximum and minimum is the 6 angstrom. We know that for the order of n is equal to 2, so n is equal to lambda by n lambda. Put this value, lambda value, order value, and d lambda value, we got the value 491 is the second orders number of minimum number of lines are present there. Let's see the examples. Separations of sodium light, lambda is given 5893 angstrom in the second order spectrum of a plane transmitting grating having 5000 lines per centimeter is 2.5 minute of an arc of normal incidence. Find the difference in wavelength between the two yellow lines. So given is the n is given 500 lines, that is 500 lines per centimeter, and the order is n is equal to t. For the second order n is equal to 2, lambda is given 5893. We know that the for value a plus b is equal to, here is a plus b equal to per centimeter is given, so it can be converted into meter. A plus b is equal to 1 by n, that is 2 into 10 to the power of minus 6. Sin theta, we got a plus b sin theta equal to 2 lambda for second order, so its value is 2 into lambda value and a plus b value, and put this and get 0.5893, and cos theta is equal to square root of 1 minus sin square theta, that is value, put this value 5893 here, so we get 0.8079. So move further. Given that d theta, some angle is given, arc angle 2.5 minutes converted into radian, so 2.5 into pi by 180 into divided by 60 means 2.5 into pi divided by 60 into 180, it gives the 0.7273 into 10 to the power of minus 3 radian. Put this value d theta by d lambda n by a plus b cos theta, or d theta value, so d lambda is equal to a plus b cos theta d theta into 2. A plus b is given, a plus b value is given 2 into 10 to the power of minus 6. Cos theta is 0.8079 and d theta value here is there, so 0.72 into 10 to the power of minus 3. So at last we got the value 5.876 angstrom. This is the separations of the wavelength. Let's move further. Two spectral lines with average wavelength of 6000 angstrom are resolved in second order. Two spectral lines with average wavelength of 6000 angstrom are resolved in second order in grating having 5000 lines per centimeter. The least width of the grating is 2 cm. Find the difference in wavelength of the lines. Here is given number of lines per centimeter. 1 centimeter there is a 500 lines. But grating the least width of grating is 2 centimeter. So the total number of lines is 2 into 500, that is 1 centimeter is 500, 2 centimeter it's a 1000. For the order, find the difference of the order, second order. So n is equal to 2, lambda is given 6000 here, lambda is here and converted, and find the d lambda question mark. For the resolving power, so the resolve of the grating is given here, so resolving power formula can be used. Resolving power lambda by d lambda is equal to n, that is order, into number of lines, means d lambda is equal to lambda into n lambda. Put this 6000 lambda value, n value, then we get the 3 angstroms, and this is the d lambda. The difference in the wavelength of the line is, a grating has 1100 lines on it. What is the difference between the two wavelengths? Should have just resolved in the first order of spectrum in the region of wavelength of 660 nanometer. We know that d lambda by lambda 1 by lambda n, that is, so d lambda value is given, lambda is value is given, lambda value is given, and small in first order, capital in 1100 lines, value is 6 into 10 to the power minus 3, and that is 6 angstrom is the difference between the two wavelengths is resolved. Similarly, a grating, next question example, a diffraction grating has a 15 centimeter of surface rolled with 6000 lines per centimeter. What is the resolving power of the grating of first order? So here calculate the resolving power. So n for the first order, n is equal to 1. Here is there is a one grating. If it is 1 centimeter, there is a 6000 lines per centimeter. But grating has a 15 centimeter surface, means the number of lines is 15 into 6000, that is 90,000 lines per 15 centimeter, not centimeter, per 15 centimeter. So resolving power is just multiply this one, resolving power lambda by d lambda, so n into n, that is 90,000. 1 into 90,000 means 90,000 is the resolving power of the grating. A plane grating of width, next one, a plane grating of width 2.5 centimeter is found to just resolve two wavelength differing of 6 angstrom in second order if mean wavelength is 5893 angstrom. Calculate the grating element. So given here is the d lambda 6 angstrom is given here, that is 6 into 10 to the power of minus 10 meter. For the second order, n is equal to 2, wavelength is 5893 angstrom. Resolving power is, we know the formula, lambda by d lambda is equal to n into n. Total number of lines, n is equal to 1 by n, that's to put this value, 499 number of lines are present there. So grating element a plus b is equal to 1 by n as usual, as we know that, but it's of a 2.5 centimeter grating, 2.5 centimeter width of the grating, hence 2.5 into 10 to the power of minus 2. So number of lines is 491, so a plus b is 1 by n, that is 0.0000509 meter, that is 5.09 into the power of minus meter. And these are the some related problems are given here. You just solve it and make stop and give pause to it, and then you can solve these problems. Answer is also given here, so you are the try to solve. This is a very important questions for the Davanagere University about the. So this is about the physics fourth paper of Davanagere University. physics, some problem will solve. So mostly for the 8 marks has been given in the examinations about this problem. Be study well, and also please subscribe my channel Dada Periods in the YouTube, so you can get some important topics unrelated physics of Davanagere University, so you can be study well. All the best. Okay, thank you.